Check it.
Okay, welcome back. Today we're going to be starting up graphing rational functions. So we already have graphed a simple rational function, which is this one right here, the reciprocal function, y equals 1 over x. Now this function I have over here, this example here, you can see it's the same function, but it's got a shift of down 2 and a shift of 1 to the left. So left 1, okay? And hopefully you learned in the last section that what you're supposed to do is draw your asymptotes first and foremost. So if we're going to move everything down 2, we're going to have a horizontal asymptote. The new x-axis, so to speak, is going to be down 2 from where it was, from here to here. And then left 1 means your new vertical asymptote is to the left 1. So that's your new y-axis. And then where's your function? Well, your function, if you want to do a quick sketch, looks something like that maybe, right? If you want to be accurate, you have to make a table, right? So we will be making tables, or we did make tables in the last section. And the way you make a table is, well, you see it's kind of centered around this vertical asymptote here at -1. So you know -1, you're not going to get a value because it does not exist on this red line. But you can go a little bit to the left like -2 and -3, a little bit to the right like 0 and 1. You can find these numbers and you can have a more accurate sense of where this graph is, right? But I just drew a quick sketch because that's not important at this very moment. What's important is to understand something. A rational function is special because it has these things. It has asymptotes most of the time, okay? And we'll be looking for where those are. Now that was really easy right here, but there are more methods for finding asymptotes coming up. Also, they have X and Y intercepts. Okay, now we know how to find intercepts, X and Y. An X-intercept would be right here, where you cross the x-axis. That's an X-intercept. And a Y-intercept is right here, where you cross the y-axis, right? Y-intercept. And the way you find an X-intercept is you make y 0 and you solve. The way you find a Y-intercept, you make x 0 and you solve, right? Remember that? The finger method. You make 1, 0, you find the other one. So we're going to be finding intercepts. And there's one more thing we're going to be finding, which actually isn't on this picture here. It's holes. Okay, and we'll talk about that in a few minutes. So how do you find vertical asymptotes and holes? Vertical asymptotes and holes happen when you have a 0 denominator. Okay? So take a look at this first example here. We have a rational function. Once again, rational just means fraction, where you have a function on the top and a function on the bottom, right? You have an algebraic expression up here, another algebraic polynomial down here, and the bottom one is the one that causes problems because you can't have a 0 denominator. You can have a 0 top all day long, but you can't have a 0 denominator. And you can see hopefully pretty clearly that right away, x equals -3 is a problem. Your domain cannot include x equals -3. So it's all real numbers except x equals -3. Now, x equals -3 is either, okay, a vertical asymptote, okay, vertical asymptote, or it's a hole. And what we're going to do right now is figure out how do you tell the difference between a vertical asymptote and a hole. Because no matter what, x cannot equal 3. So you got this function here at x equals 1, 2, 3. It's doing some stuff over here, it's doing some stuff over here, but at x equals 3 right here, it cannot exist. So either there's a dotted line that you're going to draw, which is called a vertical asymptote, or the function goes right up to it, then disappears for one point like that, and then continues, and that's called a hole. So which one is happening here? Well, the way you can tell is this. You fully factor everything. So you can see the top here is factorable. So let's write the function in factored form. Let's write it as f of x equals, and on the top it looks like reverse FOIL should do the trick, and on the bottom it's already factored. The top is going to be x and x. Two numbers that multiply to give me -6, I add to give me -1. So two numbers that multiply to give me 6, I have a difference of 1 would be 2 and 3. The bigger number is the sign of the second term, so negative is on the 3 and positive is on the 2. There we go. Now, take a look at this. Does anything cancel out? No. So that means that no matter what happens here, we cannot cancel out the bottom. If you could cancel this out, this would be a hole. But since you can't cancel it out, it's an asymptote. So hole versus asymptote. Worst monster movie ever. Can you cancel out the bottom? If you can, that means the whole brick wall thing here is not going to be a brick wall. It's just going to be a little hole. But if you can't, the brick wall lives. Okay? This thing will, so in this case, we could not get rid of the thing on the bottom creating the problem, so it's going to be a big problem. It's going to be a vertical asymptote. Okay? And that's how we know. So right away, we know we have a vertical asymptote at x equals -3. And we saw that on Desmos. Okay? There it is. This is x equals -3 right here. Okay? And you have a vertical asymptote going through x equals -3. How about this next one down here? This is almost the same function, except this time the denominator is x minus 3 instead of x plus 3. See the difference there? So let's try this one now. Once again, fully factored form, right? So we're going to write this in fully factored form. The top can be factored. In fact, it's the same top as before, so it's x plus 2, x minus 3, and the bottom is x minus 3. Now, before you do anything else, write down your domain restrictions. Your domain restriction is that x cannot equal what this time? Well, what would create a 0 in the bottom here? Not -3. This time, +3 would be a problem, right? Because if you set the denominator here equal to 0 and you solve x minus 3 equals 0, you get x equals 3. And you don't want the denominator to equal 0. So if x was +3, this would be a 0, which is bad. So your domain restrictions, d restricts, okay, is that x cannot equal 3. This is either a hole or an asymptote. Which is it? Well, like I said a minute ago, if you can cancel out, and once again, you have to write this down before you do any canceling. If you can cancel out the thing creating the 0 on the denominator, then it is a hole. If you can't cancel it out, it is an asymptote, okay? Can you cancel this out? Yes, you can. This is what's called a removable discontinuity. And a removable discontinuity is also known as a hole. And this is when you have something that's causing a problem, but you can also cancel it out. So you can get rid of most of the brick wall, but you just can't get rid of that one little hole where, because x can never equal 3. Even if you cancel this out, this still lives. This is still there. So let's take a look on Desmos and go to this one now. This is the second example. And if you look at this one, that's interesting. It's shaped like a line. Do you notice that? Like, look at this is the other one. The other one had a funky shape to it, right? Had 2 stems to it. Sorry, 2 branches to it rather. This one's just looking like a line, just like a regular garden variety line. But we know that x cannot possibly equal what? 3. But it looks like it's fine, right? It looks like there are no problems here. But there is a problem, because watch this. As I drag along here, there's the X-Intercept. Drag along, there's the Y-Intercept, no problem. But what's the x value that we know we cannot have? 3, right? Well, here's x equals 1. Okay, x equals 1. X equals 2, right there, 2 comma 4. And what is the what happens at 3? X equals 3. Boom, look at that. Now, if you're looking at this on a phone, you probably can't read it very well, but so zoom in if you can. But this says 3 comma undefined. And if you notice, it's turning into a hole. There is a hole right here. See, Desmos will not draw the hole for you, but if you know where the hole is, it will confirm it for you. So there is a hole in this function. Not a vertical asymptote, okay? There's not the whole brick wall dotted red line going up and down here, but there is a hole in the function because there's no way you can plug in a 3 into this function. So this function is essentially a line with a hole in it. So if I go to sketch it over here, what we have here is a graph. We have a line. Here's x equals 3. And we have a line going up to there, a hole, and then it continues on. So there is a hole at x equals 3. Because there's no way you can plug a 3 in here without getting a 0. But you can factor and cancel out the discontinuity. This is what causes the discontinuous. So continuous means that there's no holes. Obviously, there's a hole when you have an asymptote. There's a big hole, right? When you look at this, there's a pretty big gap here, right? This is not continuous because all in here, there's a gap right there, right? And for this function here, even though it looks continuous, it looks like there's no holes, there's actually a hole right there at 3. Okay? These are called discontinuity. So what we're really doing here is we're trying to figure out what kind of discontinuity is happening here. Is it a hole or is it an asymptote? Hole versus asymptote coming to a theater near you. Okay, so in this case, it's a hole. How do we know? Simple. After we factored, we were able to cancel out the discontinuity. So it's a removable discontinuity, and a removable discontinuity is also known as a hole. Here's a function. X plus 5 over x squared minus 25. Once again, you need to put this, well, in fully factored form, and you need to write down the domain restrictions. Well, I think we need to factor before we can find the domain restrictions, so let's factor first. The top is already fully factored. The bottom is a difference of squares. So a difference of squares, x squared minus 25, you would factor it how? Well, x plus 5, x minus 5. That's how you factor a difference of squares, right? So it's x squared and 5 squared, so it's x plus 5, x minus 5. Now look at this. Where are the discontinuities? Where are the places where the function has a zero denominator? Okay, domain restrictions, in other words. You can't put in an x equals negative 5 because then this would equal 0. And you can't put in x equals positive 5 because then this would equal 0. So your two domain restrictions are x equals 5 and x equals negative 5. Now we play the game. Is it a hole or is it an asymptote? All right, well, let's take a look. There are two discontinuities here, two discos, okay? There's a disco here and a disco here. Can you cancel out x minus 5? No. This cannot be canceled out because the top is not x minus 5. So this is permanent, not removable. This is permanent. This is going to be an asymptote. There's an x plus 5 over here. Can you cancel that one out? Yes, you can. This one is removable. Okay, it's removable. So this is a hole. You can see that this will cancel out. So there are still two discontinuities, but one of them is going to be an asymptote and one of them is going to be a hole. Now, where is the hole and where is the asymptote? Well, the hole is where this thing equals 0. So the hole, there's a hole here at x plus 5 equals 0. You need to set it equal to 0. And there's a vertical asymptote, V asymptote. We're going to talk about horizontal asymptotes later. Okay? The vertical asymptote is happening at x minus 5 equals 0. And you solve each one of these, which is really, really quick and easy. This is x equals negative 5, and this is x equals 5. Now we know where the asymptotes and the holes are. Let's take a look on Desmos and just see if that, if our picture verifies that. And you can see that's true, right? There's a vertical asymptote at x equals 5. We also said that there was a hole at x equals negative 5. No holes, off to infinity and beyond, nothing there. How about on this side here? Nothing, everything's good, everything's cool. Except when we get to 5, there it goes, negative 5 comma undefined. Why? Because if you plug in negative 5, you get a problem. But it's not a big problem, it's a removable problem, so it's just a small hole rather than a big asymptote. Now we're going to construct a couple of functions. So I'm going to actually ask you to write your own function now. Could you write the equation of a function that has a vertical asymptote at x equals 1 and a hole at x equals 4? Okay, I want a function with a vertical asymptote, meaning a discontinuity at x equals 1. Well, that's simple. Whatever my function is, doesn't matter what the top is, the bottom better have x minus 1. Why? Because if you plug in a 1 here, that creates a 0. So that's how you create that discontinuity. How about another discontinuity at x equals 4? Well, that's easy enough. Just do x minus 4 here. Now you can see my denominator is 0 at two places, x equals 1 and x equals 4. So these are both discontinuities now. But I want one of these to be a hole, okay, meaning removable, and I want one to be an asymptote, which means permanent. Well, that means I don't want the x minus 1 to cancel out from anything, but I do want the x minus 4 to cancel out. The only way to make that happen is to put an x minus 4 on top. And there you go. That's it. Can you write the equation of a function who has an asymptote at 1, a hole at 4, but also has a y-intercept at 0, 5? So a y-intercept of 5. How do you find a y-intercept? You make x 0, right? So let's look at the function that we have here, because this already has the right hole and the right asymptote. Let's see if it has the right y-intercept. Okay, plug in 0 for all the x's and you'll find the y-intercept. So y equals, and this is now 0 minus 4, right? And this is now 0 minus 1, okay? And this is 0 minus 4. And now the question is, what is this going to be? Well, it's negative 4 on top. This is negative 1 times negative 4, which is positive 4. So this is going to be negative 1. This is not 5, right? We want it to be 5. So how could I make this be a 5? Well, now that I know that the y-intercept would be a negative 1, really all I have to do is figure out a way to multiply this by -5, -1 times -5 will give me +5, and that's what I want. So I can take this same function that I have here, but I need to multiply everything by -5. So all I have to do now is just stick in a -5 right there. And if I do that, so there we go, that's our answer right there. Okay, an equation of a function with the right vertical asymptote, the right hole, and the right y-intercept. All right, so we found holes and asymptotes. Now it's time to find intercepts. Two kinds of intercepts. You have a y-intercept and an x-intercept. This is something we already know how to do. You want to find an x-intercept, you make y 0. You want to find a y-intercept, you make x 0. We've been doing it all year long. Okay, so this first one here is actually the same problem from before up top. We already looked at the graph of it. But what's the y-intercept and what's the x-intercept? So if you want to find the y-intercept, make x 0. -0 minus 6, 0 plus 3, which is the same as saying -6/3, which is -2. So your y-intercept is going to be 0, -2, or you can just say the y-intercept is -2. There's your y-intercept. What's your x-intercept? Your x-intercept is what you get when you make y 0. Now, when we say y, we also mean f of x, so making this a 0. So you're going to have to set the y equal to 0. So you get this now. So for the x-intercept, how do we do this? We take this x squared minus x minus 6 over x plus 3, and it used to be equal to f of x, but we want f of x or y to be 0, so we just set it equal to 0. So this is where people get stuck, because they have a rational equation here, and they're not sure what to do, okay? So in pre-calc and calc, we do this a lot, and I say this over and over again so that my students will remember it. I'm going to say it to you guys. When you have a fraction, the value of the fraction is 0 only when the top is 0. Don't worry about the bottom. So in this case, you can completely not think about the denominator. It doesn't matter. The denominator can be anything. It doesn't change when this fraction equals 0. A fraction equals 0 when its numerator equals 0. So that's what's going to make this a lot easier than it looks. All you have to do is worry about the top. So only solve x squared minus x minus 6 equals 0. That's it. That's going to tell you where the whole fraction equals 0. When the top is 0, the whole fraction is 0. Why? Because simple. When you have a fraction with a 0 on top, it doesn't matter what the bottom is, it's going to be 0. So all you worry about is when is the top 0? The bottom can never be 0, so that's not something you have to worry about. Okay, so only worry about when the top is 0, and the top is 0 when this thing right here equals 0. And you can see this is factorable. We factored it a few minutes ago. And when does that equal 0? Well, 0 product rule. And that means setting this equal to 0, this equal to 0. So we get x-intercepts are x equals -2, right? And x equals +3. And let's take a look. Do we have an x-intercept at +3, -2, and a y-intercept of -2? Let's take a look. Right there, what's that? That's +3. What's that? That's -2. And what's the y-intercept? -2. Perfect. Okay, we found all three intercepts just by using the methods that we have already learned. Okay, and that's it. Let's try it again. Okay, let's try it again with this one here. So we want to find the x-intercept. We make y 0. So you're just going to set this equal to 0. You're going to set this fraction equal to 0. Fraction equal to 0, remember the rule. A fraction equals 0 when its numerator equals 0. So that means all you have to do is take the numerator only and set it equal to 0. X-intercept is -5 or -5 comma 0. That was nice, quick, and easy. Okay, so we found the x-intercept is -5. Now we want to find the y-intercept. Now the y-intercept is what you get when you make x 0. And now just put in a 0 for all the x's. So this is going to be, well, the top is 0 plus 5, so the top is 5. This is going to be a 0. This is 3 times 0 squared, so it's just 0. So it's 5 over 1. So your y-intercept is 5. So there you go. You're going to have a y-intercept of +5, and you can have an x-intercept of -5. So we know how to find asymptotes, we know how to find holes, we know how to find y-intercepts, and we know how to find x-intercepts when it comes to rational functions. Horizontal asymptotes. Yeah, okay. So if you remember our y equals 1 over x, our reciprocal function, the most basic rational function there is, you had a function that did this in the first quadrant and did this in the third quadrant. It had a vertical asymptote right here, right? Your y-axis was a vertical asymptote, but it also had a horizontal asymptote that it could not cross. Now, there is a subtle difference between horizontal and vertical asymptotes beyond the direction, obviously. A vertical asymptote, when it's there, is a brick wall. You cannot ever cross a vertical asymptote. A horizontal asymptote is, sometimes it can act like a brick wall, like you can't cross it, and sometimes it just kind of guides the function. It tells the function where to end up. Okay, so take a look at this picture right over here. There are two vertical asymptotes, one at x equals -5, brick wall in other words, and one at x equals 1, another brick wall. You can never cross these vertical brick walls. There's a horizontal asymptote right here as well. But you see the function actually crosses through the horizontal asymptote, and then it kind of hugs it and settles in. So a horizontal asymptote is not exactly a brick, it's not an impenetrable brick wall the same way a vertical is. Verticals you can never go through, okay? Horizontals you might go through, but you're gonna stay close to it, you're gonna hug it, okay? So this branch right over here, it's gonna hug this asymptote and get closer and closer, and it's like landing the plane, what we talked about with logarithmic functions. It's gonna get closer and closer and closer, never actually touching, okay? So it's kind of hugging that line. This crosses through it, but then hugs it on the other side, okay? So horizontal asymptotes, you've seen them before, but now I'm making a distinction that you can actually occasionally cross through a horizontal asymptote, okay? A horizontal asymptote is not a barrier. That's what it says down here, okay? It's not always a barrier, I should say. Sometimes it is. Sometimes it acts just like a vertical asymptote, but a lot of times it's just like here. Here's an example of a vertical asymptote that you don't cross, okay? You have vertical asymptotes and horizontal. Here's a horizontal asymptote you don't cross. You are trapped between the asymptotes and you don't cross them. Whereas here, you actually see a function that does cross, okay? So don't get too confused if you see yourself crossing through a horizontal asymptote. If you're plotting points, you make a table, and your table makes a graph that goes through and then hugs this way, that's okay. It is possible. So we know how to find vertical asymptotes. We just look for where the denominator equals 0, right? And that's how we find holes in asymptotes. How do you find horizontal asymptotes? Well, there's a rule here, the rule of 3, okay, or a 3-pronged rule here. Here we go. Top heavy, bottom heavy, balanced, okay? Here's what this means. Every rational function has a function on top and a function on the bottom, so to speak. Okay, you have a polynomial on top, a polynomial on the bottom. For example, y equals x squared plus 3x plus 5 over x plus 2. What's the power on the top? This is a power of 2 on the top. What's the power of the bottom, the degree of the bottom? It's a degree of 1, power of 1. If the top power is bigger than the bottom power, I'm going to refer to that as being top heavy. If the function is top heavy, meaning the top power is bigger than the bottom power, there is no horizontal asymptote. So right away, you look at this, no horizontal asymptote. Why? Because the power on top is bigger than the power on the bottom. Done. What about if you flip this upside down? Now the power is 1 on the top and a power of 2 on the bottom. This is what I refer to as bottom heavy. And if you're bottom heavy, then your horizontal asymptote is the x-axis, y equals 0. The last one is what I call balanced. Do the top and bottom have the same power? So an example of that would be y equals 3x squared plus 2x plus 1 on top and 5x squared minus 4x plus 3 on the bottom. Okay, what's the power on top? It's a power of 2. What's the power on the bottom? Also a power of 2, x squared, x squared. The power is balanced. Top and bottom, same power. So what is there a horizontal asymptote? Yes, there is. It is going to be simply take the highest power term on the top and divide it by the highest power term on the bottom. So take 3x squared and divide it by 5x squared. The x squares cancel out and you get y equals 3/5. That's going to be your horizontal asymptote. Okay? It's going to be a horizontal line, y equals 3/5. So if you had a graph here, and let's say this is y equals 3/5 right there, it'd be that horizontal line right there. And that's it. Those 3 things, that's how you find horizontal asymptotes. Top heavy, bottom heavy, and balanced. Okay? Look at the function. If the top has a higher power, no vertical asymptote. If the bottom has a higher power, then it's y equals 0. Done. If they both have the same power, just look at the two lead terms, the two terms with the highest power of x, take those and divide them. And whatever ratio you get of the two highest terms, that's going to be your y equals line, which is your, what do you call it, your horizontal asymptote, okay? So some of these functions you're going to notice are from before. Once again, for the third time, let's visit this function here. We already found its asymptotes, its holes, and we already found its X-intercept and Y-intercept. However, does this have a horizontal asymptote? Well, it's top heavy. So that means no horizontal asymptote. How about this one here? This one has a power of 1 on the top and a power 4 on the bottom, which means it's bottom heavy. If it's bottom heavy, do you remember what it was? The horizontal asymptote is y equals 0. How about this one here? This one has the same power, 3x to the first power and 6x to the first power, same power on top and on bottom of x. Okay, there's no higher power on either. So this is what I refer to as balanced. This is all not in the textbook, by the way, just my own creations here. So what's your horizontal asymptote? Your horizontal asymptote is y equals, because it's going to be a line, it's going to be a horizontal line. Horizontal lines have the equation y equals a number. Well, what number is it? Well, once again, like I said, take the two highest power terms here and just divide them. The x's cancel out and 3 over 6 gives you 1/2. And there you go. Okay, this next example here is going to tie everything together. So it's a kind of a basic example, but I think it'll do the trick. Let's take this function right here and find all of the important things about it. The asymptotes, the holes, whatever it's got. Let's see. Okay. So first of all, before we do anything, make sure it's in fully factored form, which it already is. So we don't have to do anything to make it fully factored. And then you look at it and say, all right, what are the domain restrictions? Well, clearly x cannot equal what? -2, right? Okay, x cannot equal -2. Now, after you've done that, you go to cancel out whatever you can cancel out, but nothing cancels out. So you have a domain restriction, meaning you have a discontinuity, x equals -2, and you cannot cancel it out because, by the way, you can't do this. No. Okay? If you can't factor it out, you can't cancel it out. So you cannot factor an x out of the bottom, you cannot cancel an x out of the top. So that means x equals -2 cannot be canceled out. It's a permanent discontinuity. So this is a vertical asymptote. We have a vertical asymptote at x equals -2. No holes because nothing canceled out. What's the X-intercept? The X-intercept is what you get when y is 0. So set your fraction equal to 0. And once again, a fraction is equal to 0 when the numerator equals 0. So don't even worry about the denominator. When is this equal to 0? Well, X-intercept at x equals 0 at x equals 0. X equals 0. Okay, there it is right there. What is the Y-intercept? Well, if this is y, you make the x's 0. Y equals 0 plus 0 plus 2. 0 over 0 plus 2. Well, 0 over 2 is just 0. So the Y-intercept is 0. So you actually have an X-intercept at 0, 0 and a Y-intercept at 0, 0. Basically, that just means this thing goes to the origin, right? Okay. So the function goes to the origin. It has a vertical asymptote at at x equals -2. No holes. And does it have a horizontal asymptote? Is it top heavy, bottom heavy, or balanced? Well, it's got an x on the top and an x on the bottom. It's balanced. It's not higher power on the top or the bottom. So what you're supposed to do is take the highest power term on the top, which is x, and divide it by the highest power term on the bottom, which is also x. And x over itself is going to cancel out, and that gives you y equals 1. So you have a horizontal asymptote of y equals 1. Now with that information, you can draw a quick sketch. Let's say that's y equals 1. You have a horizontal asymptote going through y equals 1. You have a vertical asymptote going through x equals -2. Let's say that's right there. So vertical asymptote going through x equals -2. So that's how easy it is to find your asymptotes. You have an X-intercept and a Y-intercept. In other words, they're both 0, 0. They're the same point. So your only intercept is this right here, the origin. So you have a function going through the origin, okay? And now that's everything that we can tell from looking at this picture. Now, how do you find the rest of the points? Basically, you're going to make a table, okay? And when you make that table, my best guess right now without looking at the answer is that it's going to asymptote this way. It's going to asymptote this way. And it's going to be doing something similar here in here. And there you go. We've just graphed our first real, rational function, not just a reciprocal function, a real rational function with horizontal asymptotes, vertical asymptotes, holes, etc. So x over x plus 2, let's take a look at Desmos here, and let's see how good my sketch was. Okay. And yep, looks like I'm right about that. I said the only intercept was 0, 0. There it is, 0, 0. Okay. There's a horizontal asymptote at y equals 1. And you can see it's actually, yep, that is good. That is, if you zoom in more, you can see that it's not touching. It's getting close, but it's not actually touching. Okay, so yeah, both asymptotes are correct and both intercepts are correct. And there are no holes. There's one last topic here that's honors only. So if you're an honor student, you're going to want to stick around for this last part here. If you're in an academic class, you can stick around if you're curious, but otherwise you don't have to worry about this on your quiz. Slant asymptotes. There's one more kind of asymptote that we haven't covered yet. We talked about vertical, we talked about horizontal, but sometimes you actually get an asymptote that's slanted. When does that happen? Well, remember we talked about top heavy and bottom heavy? If you're top heavy by exactly a power of 1, you're going to have what's called a slant asymptote. Okay? So, if the top function is exactly 1 power higher than the bottom, technically it's top heavy, but not like by 3 or 4 powers, just by 1 power. If the top function is 1 power higher than the bottom, you're going to have an asymptote, but it's going to be a slant asymptote. So if you remember, if we go back to the rules up here, okay, top heavy, bottom heavy, what we said was that if you were top heavy, there was no horizontal asymptote. So you might be saying, hey, I thought you said there's no asymptote if it's top heavy. No horizontal asymptote, but there is a slant asymptote. Slant is not horizontal. Slanted, okay, like it's an oblique line, it's got a slope to it. If you're top heavy by just 1 power, you'll have a slanted asymptote. Okay, so let's try this example here. You can see that this example here is top heavy by a factor of 1. This is x squared, this is x to the first power. So it's top heavy by just 1. Okay? So you might say, well, how do you find, the slant asymptote that I'm referring to here? Well, the way you find the slant asymptote is to divide the top by the bottom. Okay? Now, if you remember with the balanced, we had top heavy, bottom heavy balanced. With the balanced, you just divided the first 2 terms, the highest power 2 terms. Now you have to divide the entire thing. So divide this whole thing by this whole thing. Now you could use long division, but this is in the form of x minus c. So go ahead and use synthetic division. It's much, much easier. So your c is -2. You can see that hopefully, right? And then this is 1, -1, 6. So here we go. You drop your 1. -2 times 1 is -2. This is +3. -2 times -3 is +6. And this is a 0. So there you go. What you get here is x minus 3. When you divide this, you get x minus 3. So your slant is going to be y equals x minus 3. So let's take a look at this graph on Desmos and see if y equals x minus 3 makes any sense. Here it is on Desmos. This is the function right here, f of x equals x squared minus x minus 6 over x plus 1. And if I write that function right underneath it here, y equals x minus 3, and make it red and dotted, like we do with all our asymptotes here, is that an asymptote? And you can see that it's definitely hugging. Like on this side, it's not touching at all, right? And on this side, it does cross it once. Like I said, that can happen, but it's still hugging it as you go off and away. Okay, if we zoom way out here, zooming out, zooming out, zooming out, you can see that dotted line and that function, they hug each other forever and ever and ever. They never deviate from each other. So even though in the middle here it looks like it's going off track, as you zoom out, you can see that they are definitely guiding each other. Okay, that asymptote, that slant asymptote, just like a horizontal asymptote, you can cross it, but you will hug it forever as you go out to infinity. So as I zoom out and zoom out and zoom out and zoom out and zoom out, okay, this is 500, this is 1,000 now, they're still connected. They're still hugging to the point where you can't even see them anymore. They're like one line now. Okay. Let's try one last example here. And by the way, all the other stuff is the same. You want to find the X-intercept, the Y-intercept, all the other stuff is the same, but the horizontal asymptote, you look at it and say, hey, there's no horizontal asymptote. But once again, honors kids, you have to remember, if it's top heavy by 1, if it's top heavy by 2, 3, 4, any other number, it's no horizontal asymptote and no asymptote, period. But, well, no horizontal or slant. But if it's top heavy by 1, you got to look for the slant asymptote. So here we have something that's written in factored form, and we have this. So we're going to have to expand this. If we multiply this x plus 1 times itself, we get f of x equals x squared plus 2x plus 1 over x plus 2. And now that, okay, you can see that's a power of 1, that's a power of 2. It's top heavy by 1, it's a slant asymptote. So once again, you can do the synthetic division here. That's c equals 2. And we have 1, 2, 1 here, okay? And this is probably not going to come out to be an even thing, so there might be a remainder, sorry. That's fine. Drop your 1. This is -2. That's going to be 0. That's going to be 0, and there's going to be a 1 there. So this is your remainder. So the fact that you get a remainder here is not a problem because we're going to ignore the remainder. All right? So remember, this used to be the x squared column, this was the x column, this was the constant column. So when you do your synthetic division, this becomes the x column, and this is the constant column, and this is the remainder. Okay, we're going to ignore the remainder, and that means we have x plus 0, which is our, our result here, if you don't have the remainder. So y equals x. There you go. That's your slant asymptote. And now we'll go ahead and do all the rest of the stuff that we're supposed to do as well. Holes and vertical asymptotes. Where do you look for holes in vertical asymptotes? In the denominator. Well, the denominator equals 0 when x equals -2 here, right? That's your domain restriction. So x equals -2 is the only place you can have either a vertical asymptote or a hole. Now, since the x plus 2 doesn't cancel out with the numerator, okay, once you factor the numerator, if you can cancel it out, it's a hole. If you cannot cancel out, it's a vertical asymptote. So this is a vertical asymptote right here. So you have a vertical asymptote. So what do we have here? We have a horizontal asymptote of y equals x. We have a vertical asymptote of x equals 2. What about the x-intercept? Happen when y is 0. Now this is a fraction. Your y here is a fraction. So you set the top equal to 0 only. And then you set the top equal to 0. You can see that you have a y-intercept an x-intercept at x equals -1. For both of these, it's the same thing. -1 would make the top 0. Okay? And what about y-intercept? Y-intercept happens when the x's are all zeros. So that would make this 1 times 1, which is still 1, over 2. So 1 over 2 is y equals 1/2. So maybe I should write this a little bit differently. Instead of x equals -1, it should be -1 comma 0. And this should be, the y-intercept should be 0 comma 1/2. So we got our x-intercept, our y-intercept, vertical asymptotes and holes are covered. I wrote the horizontal asymptote. There's actually a slant asymptote here. And at this point, you have all of the data you need to start sketching your graph. So you can go ahead and, let's see here. -2 is a vertical asymptote. So we'll go back to here and we'll draw our dotted vertical asymptote. Remember, that's a brick wall that you cannot get through at all. We also have y equals x, which is our slant asymptote. Y equals x is, if you think about it in terms of y equals mx plus b, is y equals 1x plus 0, right? The slope is 1, the y-intercept is 0. So you're starting at the origin, you're going up 1 over 1. You're starting at the origin, you're going up 1 over 1, up 1 over 1. It's that diagonal line, y equals x. If you remember when we did inverses, that's the line you reflect across, right? So there's your slant asymptote. We have a vertical asymptote, we have a slant asymptote. We know we have an x-intercept at -1 comma 0, so there's an x-intercept right here. And we have a y-intercept at 1/2, so that would be right here. Okay? So that's everything we can glean without making a table. And if I had to guess, then, well, okay, we're going to go through these 2 points here. You're probably you're definitely asymptoting against this line here. You're probably not crossing it though. So my guess is something like this, and maybe something like that going up this way. And there's probably another one in here as well. So what we're going to do tomorrow, that was a guess. Okay, I can go to Desmos right now and check it out, but I'm not going to. What we'll do tomorrow is make a table. and we'll get a lot more points, okay, aside from just the 2 points that we had here, and we'll know for sure. All right, so what we're going to do in the next lesson, tomorrow, day after tomorrow, whatever it is, we already have a couple of things. We already know that -1 is 0, because -1 comma 0. We already have 0 comma 1/2, right? Those are the 2 points we already have. But we can actually plug in some more points. What about +1 and +2 and +3 and -2 and -3, right? And fill in this table with your calculator, right? Plug in some numbers and get more points, and you'll see more of the function. And that's what we're going to do in the next lesson. Now for the homework, okay, if you're in the academic class, and I know the academic people probably left by now, but if you're in the academic class, you have 13 through 18, 28 through 32. It's the same homework as the honors, except there's no slant asymptotes. So you guys in the honors class, you're going to have a few extra problems where there are slant asymptotes. You don't have to graph, okay? You don't have to make the graph. Just find all of these things: the X-intercepts, the Y-intercept, there's only one Y-intercept, asymptotes, and holes, okay? And the only difference is that for the honors class, you have to worry about slant asymptotes, whereas the academic class, you don't have to worry about slant asymptotes. Okay, we are done. See you at the next video.
Check this.